Hello, everyone, and welcome to Virtual Planetarium, exploring space, part of our MOS at Home programming. My name is Janine. My pronouns are she and her, and I'll be your moderator today. That means I'll be reading some of your questions and responses, which you can submit below using the Q&A button at the bottom of your screen here in the Zoom meeting. And if you'd like to see captions during today's program, you can click on the closed captions button at the bottom of your screen and select Show Subtitles. If you're joining us on Facebook or YouTube, hello, welcome. We're so excited to have you here. Unfortunately, I'm unable to see any of your comments at this time. We're so delighted to have all of you here, whether this is your first time or you're a repeat visitor. Let's get ready and started and meet our guides for this journey through space.
Hello everyone, my name is Katie, my pronouns are she and her, and today I will be talking you through the solar system today, but I will just be doing the talking.
Hi everybody, my name is Talia. I use she, her pronouns, and I will be flying you through the solar system today.
Sounds good. So today we are going to be talking about magnetism in the solar system. So what planets have magnetic fields, which ones don't, which ones have really weird magnetic fields or really weak ones. So we're going to kind of go on a tour of the solar system, and we will start around the Earth. So Talia, you can bring us into space. Awesome. We are using Worldwide Telescope today, so that is a free program that you can download if you have Windows. You can go to worldwidetelescope.org/download, I believe. We'll have the link for you at the end if you're interested in playing around with it yourself. So we're going to start by looking at the Earth and the Earth's magnetic field to kind of give us an example for what we're used to, and then you can kind of compare it to some of the other planets. But even before we go into that, we have to back up and talk a little bit about the most fundamental pieces of physics and astronomy. So how are magnetic fields created? And so for that, we've got to talk about the atom. So atoms make up everything. They're the smallest unit of matter that can actually form a chemical element. So if you have a hydrogen atom and you take apart that atom, it is no longer hydrogen. It's the smallest thing possible. And within atoms, you have particles like protons and electrons and neutrons. So protons are neutrally charged, so they don't have a positive or negative charge. Protons are positively charged and electrons are negatively charged. And sometimes atoms can get electrons stripped away, or maybe they gain an electron. But either way, any kind of transfer of electrons like that will create a charged atom or molecule. So if you have an electron that has been taken away, it is now positively charged. If you have an added electron, it is now negatively charged. So if you have these charged particles or charged atoms or molecules moving, that creates an electrical current. Electrical currents then induce magnetic fields. So that's kind of the basics behind how magnetic fields form. And so that means, because the Earth has a very strong magnetic field, it protects us from a lot of radiation out in space. It has a really strong magnetic field, which means there's got to be some source of electrical current happening inside of the Earth. So I'm going to switch over to a slide I have here of the interior of the Earth. So you can see the crust and the mantle, but we're going to be focusing on the inner part here, so the core. So at the very center of the Earth, we have a solid core of mostly iron and nickel. And then right outside of that core, the outer core, is liquid iron and metal. And that's going to be kind of where the electric current is being generated. So the core of the Earth is under really high pressures and has really high temperatures. And so there's this process called convection happening in the core of the Earth, where the material is heated and then it rises, and then it cools and moves back down. So you have the liquid and the iron, or sorry, the liquid iron and liquid nickel that's being heated, and it's moving throughout the outer core. And it's moving because of the heat source and also the fact that the Earth is spinning. So this motion of the liquid iron and nickel is causing little pockets of positive and negatively charged regions to appear within the liquid. And so now you have an electric current in the core of the Earth. So that's kind of where the magnetic field is being generated from, this electric current that's in the center of the Earth. And this is called a dynamo. It's kind of like a generator. And because there's so much of this material inside of the Earth and it's all moving and the Earth is spinning, it generates a very strong magnetic field. And so now I will show you what the magnetic field of the Earth looks like. So you have a North Pole and a South Pole, and the magnetic field itself is really just an area that kind of dictates how charges are moving, positive and negative charges are moving. So you can see that the charges would move from the South Pole of the Earth, and they move all the way up to the North Pole. And you'll notice that the magnetic poles are a little bit offset from the geographic North Pole. So when we think about the North Pole, we think about, you know, the Arctic area region of the Earth. And the magnetic North Pole is also in that area. It's just a little bit offset. So they don't have to line up, and they actually don't for most of the planets in the solar system, except for Saturn. So we'll talk about that a little bit later. Now, what's really awesome about our magnetic field is that it protects us from charged particles and radiation coming from the sun. This is called the solar wind. And so when the particles hit the magnetic field actually generates a force and causes those radiation particles to just kind of bend away. So they don't end up coming down and hitting the Earth. Some of them do. They travel along the field lines and enter the Earth at the polar regions. But for the most part, we are protected by the magnetic field. And it's one of the reasons that life is able to exist on the Earth. And it's something that we're looking for in other places when we're looking at planets orbiting around other stars. This will be a big factor in determining whether or not life as we know it could exist on one of these other planets. So very important that we have a magnetic field, but I think now we should go ahead and look at the magnetic fields of some other planets. So our first stop will be Mercury. So that's the closest planet to the sun. We don't get to travel to it very often, so this is pretty exciting. And as we are traveling there, have any questions come in so far, Janine? Or actually, I don't think there are any so far. But if anybody has any questions, please feel free to type them in the chat as we go.
No questions about space stuff, although I think we should mention about the Aurora Borealis and the Aurora Australis when you're talking about all the charged particles.
Yes, absolutely. So I was going to save a little bit of the sun stuff for the end, but just in case we don't get to it, when I mentioned that charged particles coming from the sun, so the solar wind comes in and hits the magnetic field, a lot of it's deflected, but a lot of the charged particles travel down the field lines and enter Earth's atmosphere at the poles. When they enter the atmosphere, these charged particles collide with elements that are already in our atmosphere, causing them to release energy in the form of light. So we have mostly nitrogen in our atmosphere, followed by oxygen. So those tend to be the elements that are most affected, and they tend to release green light most often, but there are other colors as well, and that's the source of the Aurora Borealis, and if you're in the northern hemisphere, or the Aurora Australis if you're in the southern hemisphere. And if you get a really strong like solar storm, for example, that's sending out a whole bunch of charged particles and radiation, then sometimes that aurora can actually stretch really far down. And so you might even be able to see it from mid-northern latitudes, maybe a little higher than that. But if you ever get a really strong solar storm, you got to look out for the aurora. They're really incredible. All right, so here we are orbiting around Mercury. Now, Mercury is the only other planet in the solar system that has a magnetic field similar to the Earth's. It is generated by a dynamo in the same way that the Earth is. So it has a liquid metallic core, probably iron. And so it also generates a magnetic field. Again, the moving currents, the electric currents that generates the magnetic field. But Mercury's magnetic field is not nearly as strong as the Earth's is. It's only about 1% as strong as the Earth's. And part of that is because Mercury is very small. So it's likely that in the early solar system days, the core kind of cooled off more quickly, just because it's a smaller planet. And so that's why the magnetic field isn't quite as strong. But there is evidence that the magnetic field around Mercury is billions of years old. And it just cooled, the core cooled and solidified a little bit more quickly than Earth's did. It is strong enough to protect Mercury. So it's very close to the sun, so it gets a lot of bombardment from the solar wind, so those charged particles things. But Mercury's magnetic field does deflect it just a little bit and kind of protects it. But Mercury also doesn't have an atmosphere. And so that's another thing that magnetic fields are really good at, is that they help protect atmospheres of planets. But because Mercury is so close to the sun and its magnetic field is fairly weak, it has a hard time hanging on to a stable atmosphere, and an atmosphere that remains relatively unchanged. Mercury does have like a temporary atmosphere that kind of happens every now and then, but for the most part, it's too weak of a magnetic field. And also Mercury's pretty small, so it doesn't have a lot of gravity to kind of hold all of the gases that would be a part of an atmosphere. So even though it does have a magnetic field, it's not to the extent that the Earth does. So that's a little bit about Mercury, but now let's head to Venus. So Venus is a really interesting planet for many, many reasons, but Venus doesn't actually have a magnetic field like the Earth or Mercury does. There is no internal dynamo going on. Planetary scientists do believe that it might have a liquid iron core, but the issue is Venus doesn't spin very fast. Its day takes over 240 Earth days to complete, which is actually longer than its year. So it's not rotating very quickly at all. So all of that material in the core, it's not really moving around at all. And so it's not generating the electric current needed to induce a magnetic field. But that doesn't mean that there's no magnetism happening around Venus, because Venus has a thick atmosphere, and at the very top of the atmosphere, there's a layer called the ionosphere. And this layer is filled with charged particles that interact with particles from the sun, charged particles from the sun. So this interaction actually causes Venus to have a kind of like a magnetosphere, but it's not quite as extensive. It's more like a comet tail. It's very minimal, but I can show you just quickly a picture of what that looks like. All right. So that's the Earth. All right, so this is more of what Venus is. It's more of a magneto tail, just kind of like a string behind Venus. And this is what it looks like. It almost looks like a jellyfish. And here's a video of how it can change over time, but it's not nearly as strong as the Earth's entire magnetic field is. And so now if you're wondering if the magnetic field, if Venus doesn't have a magnetic field, how does it have such a thick atmosphere? Which is a really good question that planetary scientists have looked at, and they have some ideas. Venus is covered in volcanoes. So there is new gas basically being pumped into the atmosphere all the time. So that's kind of one source of the material in Venus's atmosphere. But it also has a similar mass to the Earth, so it's got significant gravity. And because Venus's atmosphere is mostly carbon dioxide, which is a heavier element, it's able to just by sheer gravity kind of hold on to a lot of it. And it's also possible that the very, very weak magnetic field that Venus does have, just because of its upper atmosphere, might help protect it as well. But there's still a lot of mysteries to it, and that's actually a pretty common theme when we're talking about magnetic fields throughout the solar system. And the actual interiors of planets is still very much ongoing science. And so we're learning new things all the time. All right, so we've got the Earth, Mercury, Venus. Now let's head out to Mars, which is a very interesting planet. So now we're going farther away from the sun, farther than the Earth is. And just for some basic facts about Mars, it is smaller than the Earth. It's just over half the size of Earth. And it's about 150 million miles away from the sun. And here we are. We lovingly call it the red planet because of its kind of rusty surface features. It does have a lot of iron in the crust, so the iron combined with the teeny tiny atmosphere that Mars has makes it have this reddish color. But Mars doesn't really have a significant magnetic field, but we think that it used to in the past. So billions of years ago, currently there's evidence for water on the surface of Mars billions of years ago. Right now, it's a very, very dry desert, essentially, and it's very cold on the surface. It doesn't have much of an atmosphere. It's about, I believe, 1% as thick as the Earth's is. So, and it's mostly carbon dioxide. So it's a very thin atmosphere, very cold, at a very dry place. But astronomers don't believe it was always like that. They think that Mars used to have a much stronger magnetic field that helped Mars retain a thicker atmosphere, which then allowed liquid water to be on the surface of Mars. And part of the reason we know this is from sending spacecraft out to Mars. So the InSight lander, which was a relatively recent one that landed on Mars, is studying kind of the composition of Mars and kind of digging down into Mars to measure things like, is there any kind of magnetism happening on Mars? And it turns out there is, but it's not a dynamo like the Earth or Mercury. Mars probably once had a dynamo, but it cooled off over time, leading to a decrease in the magnetic field, and therefore it kind of lost its atmosphere. But there is evidence that there is still a little bit of a magnetic field in the southern hemisphere on Mars. So basically all of the material on the surface of Mars is relatively new. So it's not magnetized at all. But if you go really down deep into Mars, there are rocks that have, remained unchanged for billions of years that would have been magnetized from the core of Mars billions of years ago, back when it actually had a full dynamo. And so there are little pockets around the southern hemisphere of Mars where there's evidence for these kind of small magnetic fields that still exist. So no overarching protective magnetic field on Mars, but it does have these kind of little spots. And so if we ever sent people to Mars, it's going to be a really big challenge, because Mars isn't protected from radiation, charged particles coming from the sun. And that's why it looks like a deserted place today. So that is something that we have to take into consideration if we're sending people to Mars. All right, so for the outer planets, I'm going to kind of group them into two categories, because Jupiter and Saturn are fairly similar, and Uranus and Neptune are also kind of similar. But first, I will pause to see if there are any questions.
We do have a question as to whether that white patch on Mars is a pole or not.
Yes, it is. That is one of Mars's poles. The white is ice. Mars has two polar ice caps. One of them is water ice, and the other one is made up of carbon dioxide ice, which we call dry ice. And astronomers and planetary scientists believe that there is an ocean potentially underneath all of the ice at the pole of liquid water. So like almost like a sub-ice lake, which is going on there. All right, so let's see. Let's travel to Jupiter. We'll just do one of each of those groupings. So Jupiter and Saturn are the largest planets in the solar system. If you could open up Jupiter like a cookie jar, you could fit over 1,300 Earths inside of it. Saturn, you could fit over 750 Earths. So they are incredibly massive, and they're mostly made of gas, mostly hydrogen and helium gases. But as you go toward the core, there is another substance that is called liquid metallic hydrogen. And this is a fairly recent discovery. And it's a really weird substance that, scientists are still studying to figure out like what the properties of it would be. But we do know that Jupiter and Saturn have incredibly strong magnetic fields, Jupiter having the strongest in the entire solar system. And it is thought to be generated from this liquid metallic hydrogen moving in the core of the planets. So it's the electric current happening within the liquid metal is causing a very, very strong magnetic field. And part of the reason it's moving so much is because Jupiter and Saturn both spin very quickly. Jupiter's day is just under 10 hours and Saturn is around 10 hours. So they're spinning very quickly. Lots of opportunities for that material to be swirling around there. And also the core, even though these planets are far away from the sun and it's very cold out here, the more you go toward the core of these planets, the more pressure rises and temperatures as well. So helium, that's being heated as it gets close to the core, it can kind of generate like a convection similar to the Earth and Mercury. And so that is believed to be the source of the magnetic fields around Jupiter and Saturn. Saturn in particular has a magnetic field that is lined nearly perfectly with its rotational axis. So on Earth, we saw that it was offset just a little bit, but on Saturn, they're perfectly aligned. And in addition to planets, there are some moons that have magnetic fields as well. Some of them around Jupiter. Ganymede, I believe, has a weak magnetic field, but we'll have to do that for another show. All right, so our last stop today in the solar system is going to be to either Uranus or Neptune. So if you have a preference, go ahead and type it into the chat if you want to see one over the other. They're very similar, so it's easy to talk about them at the same time.
I have questions about how many moons Jupiter has.
Yeah, Jupiter's got quite a few. Last count, it is up to 79 moons. And that was after 12 new moons were discovered just a year and a half ago, I believe. So new moons are being discovered all the time. Saturn is up to 82.
And I think the majority has it at Neptune. We want to visit
Awesome.
Neptune.
All right, Talia, bring us to Neptune. I love this planet. It's got such a beautiful color to it. And so these two outer planets, Uranus and Neptune, they both have a bluish hue to them, and that's because they are made up of, mostly hydrogen and helium, but they also have a lot of methane in the atmosphere, and that's what gives them their bluish hue. So these planets, sometimes they're referred to as ice giants, and that's because inside of the atmospheres, there are water ices and ammonia ices. And a little bit deeper, astronomers believe that there are oceans, salty oceans of water and ammonia. And that's actually believed to be the source of the magnetic fields around these two planets, Uranus and Neptune. generating electric currents, creating the magnetic field. Now, what's really interesting about these two planets is that magnetic field is not very symmetrical. So instead of it originating in the very center of the planet, it's a little bit off center. So I actually have one more picture to show you. Let's look at this one. So I know there's kind of a lot going on in this graphic, but if you just look at the two bars, which are our magnets, you'll see that they're not going right through the center of these planets. So the magnetic field is stronger on one side than it is on the other. And this is probably because the magnetic field isn't coming from electrical currents directly in the core. It's probably coming from areas in the planets that are closer to the surface, and that's why they are a little bit offset. All right, so actually we do have a couple minutes. Janine, do we have any more questions coming in? Otherwise, I'll talk briefly about the sun.
We did have a question earlier on, I think it's in reference to Venus, which was, can you feel it moving since it's moving so slow?
That's a good question. So if we think about, you know, if we can feel the Earth moving, we can't really feel it moving at all because we're also traveling at the same speed that the Earth is spinning. So we can tell that we're rotating because it turns from day to night, but we can't really feel it moving. If you were on Venus, it would be similar to that. You wouldn't be able to feel that you're moving at all, but you would notice a difference between how long it takes for it to change from day to night. It would take almost a year or 2/3 of a year of an Earth year to actually see a change from day to night. So it'd be really weird.
And I think that's it. So tell us some stuff about the sun.
All right. So I keep referring to the solar wind, right? The charged particles and radiation that keeps coming from the sun. And that's because the sun is almost like one giant dynamo. It's made up of a material called plasma. And so plasma is essentially ionized gas. So it's gas that has an electric charge to it. So it can either be positive or negative. And so in the interior of the sun, it's millions of degrees in the core of the sun. And that creates another convection process. So you have really, really hot plasma that is rising to the surface, cooling, and then settling back down. So you have this motion again of charged particles. You're creating an electric current, which then induces a magnetic field. So the sun has an incredibly strong magnetic field. And when we look at the sun in different types of light, like ultraviolet light, for example, we can actually see the magnetic field lines because there's plasma traveling along the magnetic field lines. And sometimes these lines get all tangled up and snap, and they will send large amounts of charged particles and radiation out into space. So when that happens, that's a good opportunity for viewing the aurora if it's headed in the direction of the Earth. All right, well, thank you, everyone. I'll turn it back over to you, Janine.
Yeah, I think that's about all the time we had today. Thank you all so much for joining us. Thank you to Katie and Talia for taking us on this journey through space. I'll let you guys say goodbye.
Thanks, everyone.
And if you did enjoy this program, you can keep an eye out on the museum social media channels. Our Facebook, our Instagram are great places to keep an eye on what's coming up. We also post on our websites, or you can visit www.mos.org/mosathome. If you enjoyed today's presentation and would like to support more programming like this, please visit engage.mos.org/welcome to support MOS at Home. And thank you to all of you who already have. As Katie mentioned, today's program was produced using the free software Worldwide Telescope, which you can find at worldwidetelescope.org. Thank you all for joining us today.